here. Okay, so what did I say? I took a sample. Sample size was what, 40? Okay, my mean, X bar, was how much? Was 30, was that 42? And my standard deviation was 6.3. Okay, good. And let's see what the question was again. You calculate standard deviation. Is 42 mu or X bar? I wrote it there, right? It's X bar. It's a sample mean, not population mean, right? That's not the mean for all bars in New York City. It's only for the 40. It's only the average for the 40 ones that we sampled. Is 6.3 sigma or standard deviation? Okay. There's only two choices. You can pick one. It's the standard deviation, right? It says, because we got that from the sample. We don't know the standard deviation for all of the pubs in New York City. We do know it for this 40. We didn't have it. Okay, can I use it? Can I use it in place of standard deviation, in place of sigma? I can. Why? Because my sample size is bigger than 30. Okay, this is kind of like a loose rule. It's not like when we use SPSS to do these calculations, which we're going to start to do very shortly. Maybe not today, but certainly by Monday, we're going to start to use SPSS. Oh, thank God we have SPSS for some of these calculations. Once you see some of the formulas, you'll really appreciate it. Since it's not a hard and fast rule. When we use SPSS assumes that 30 is not a good rule, that we have to do special things for any sample size. Even if it's 900, that's not a big enough sample size to assume it's the population standard deviation, right? So it's always going to calculate these things based on what we're going to call the t-distribution, but that's coming up. So, but for our estimation, when we do it by hand, when we do these calculations ourselves in Excel or by hand, we're going to assume anything over 30 is a large sample, and it's something that we can use in place of the population standard deviation. Okay, so now, so standard deviation, calculate the standard error for repeated samples of size 40. Okay, so what's the standard error? Standard error is going to be equal to sigma, or we don't know that, so it's going to be 6.3, divided by the square root of the sample size. So what do we wind up getting for that? Let's give that calculation a try. Going to be 6.3. Let's see, square root of 40. I think that's going to be, I want to do that first. I'll put that into memory. And I'll clear that, and I'll put in 6.3 divided by, I feel much better if I do this out loud. So divided by memory recall is equal to about 1. Right? You guys get the same thing? Standard error is roughly 1. So let's go back here and see what the calculating 95% confidence interval for beer inventory based on this sample. Well, it's going to be, what's the 95% confidence interval for the average number of beers that are carried by pubs in New York City? 95% confidence interval is going to be, let's see, X bar plus or minus the 1.96. We're using 1.96 because the sample size is large. We'll see that's going to change shortly. Times the standard error, which is 1. So it's going to be 42 plus or minus, say, roughly 2. So it's going to be basically 40 to 44. That's our 95% confidence interval. Sure. X bar is 42. That's the average number of beers that the pubs in our sample carried. Okay. And then I'm going to multiply that by 1.96 times the standard error, right? 1.96 times the standard error, which we calculated to be 1. I'm rounding the 1.96 to 2 for our purposes. So it's 42 plus or minus 2. So what I'm saying, I'm 95% confident that the true population mean for the number of beers carried by pubs in New York City is between 40 and 44. So now, if I go out and I want to compare that to, let's say I go to San Francisco, right? And I want to test to see whether or not pubs in San Francisco carry the same number of beers as pubs in New York, right? If I go out to San Francisco, but let's say I go to San Francisco and I sample all the beers, all the pubs in San Francisco, so I know what mu is equal to in San Francisco. Well, if I set up a null and alternative hypothesis, right? My null hypothesis is the mean number of beer in New York is equal to the mean number of types of beer in San Francisco. My alternative is that they're not equal, right? San Francisco. Okay, that's my alternative hypothesis. So now let's say this is a one sample test. Why is it a one sample test? Because I'm depending on a sample to tell me the range for New York pubs, but I know what it is for San Francisco because we actually went out and surveyed every pub. So let's say for San Francisco that it turns out to be 41. Can I reject my null? Can I reject my null hypothesis in this case? No. Why? Because 41 is not outside of that range, 40 to 44. What's that? The mean number of beers carried by pubs in San Francisco is known to be 41. Can I reject my null hypothesis that New York pubs and San Francisco pubs carry the same number of beers? No, I can't reject the null hypothesis because it's entirely possible that the mean for New York pubs is 41 because we're saying we're 95% sure it's between 40 and 41 and 41's in that range, right? Now, if I had said the mean for San Francisco pubs is 39, can I reject my null hypothesis? Yes, I can, right? I can reject my null hypothesis and I can accept my alternative hypothesis that pubs in San Francisco carry more brands of beer. Okay, now the other way I could do this is to actually calculate, let's say for 39, actually calculate a p-value for the probability that I would get this extreme of value, this extreme of difference between the sample mean for New York and the known value for San Francisco. And how do I calculate that? I say z is equal to the value x minus mu over my standard error. Okay, so what's my standard error? The only standard error I have that I can use is what I knew from here, which is 1, right? And what is x? X is, say, what's the average here I have for New York? 42, minus the mu that I know, which is 39, right? So that's equal to, z is equal to 3. So if I look at, since this is two-sided, I have to consider the probability that I could be 3 z-scores to the right and 3 z-scores to the left of the mean. So what is the area that leaves 3 z-scores? The area represents 3 areas to the left. It's going to be a real small number, right? 0.0015. Okay, and that means that I also have to consider the same area to the top because I didn't know going in whether it was going to be greater or small, 0.0015. So my probability of getting that extreme of value on either side is going to be the sum of these, which is 0.003, 0.3 of 1%. So there's two ways I could look at this. One way is to see, well, this is outside of my confidence interval for New York, this known value. Okay. The other way I can look at it is the probability of getting this extreme a difference between the two of them is equal to less than 1%, 0.003, or 0.3%, which is less than my acceptable level of error, which is 0.05. Both of those are arguments for rejecting the null hypothesis. Okay, so you guys online, I made the 39 up. That's where the 39 came from. Carol, I'm not sure where's 39.8 from. Okay, yeah, it was 42 for our sample. Okay, see, so this is the idea of what we're doing. So now I'm going to throw a monkey wrench in this whole thing, right? I'm going to go back to this to the first. Now that you kind of almost think you understand this, I'm going to make it so that it's even more confusing. I can't help myself. That's just the way it is. That's the way this stuff works. There was a book in the 70s called The Peter Principle. Anybody ever read that book, The Peter Principle? Anybody know? Anybody know or remember what the Peter Principle was? Anybody online? Doesn't look like it. Yeah, this is a two-sided example. That's correct. Right. You raised it like Karen knows it. Okay. The idea of the Peter Principle was, let's say you go work for a corporation, right? And you go in the entry. Yeah, you start off on the at the bottom, right? You do a good job. What do? They promote you, right? You do a good job there. What do? They promote you. What happens if you do a good job there? They promote you. So eventually, you go through like some of the year at this job, do it well, go to the next job. Get a year at that job, do it well, they promote you to the next job. Eventually, you get to a job you can't do very well, and you stay there forever, right? So that's the Peter Principle, basically, and kind of like and you'd be amazed how often that you actually observe that in business, where you see a guy that like winds up in a job that like he's never going to get promoted, and it doesn't seem like he's never going to get fired, so he just winds up staying with a job that he just can't do well. At any rate, hopefully you'll never find yourself in that situation. Way true. Karen says way too true. Okay, so I diverge again. So let's go back on topic here. Let's take a look at this example, which is, want to know something? Let me get one. I'm tired of talking about salaries. The mean number of close friends for the population of people living in New York is 5.7. The standard deviation of scores in this population is 1.3. Okay, so it's an average of 5.3, 5.7 for the entire population. Standard deviation for this population is 1.3. So we know mu and we know sigma. An investigator predicts that the mean number of close friends for introverts will be slightly different from the mean number of the population. The mean number of close friends for a sample of 26 introverts is 6.5. Okay, so now we got to decide whether or not this really supports this investigator's point of view. I'm going to start off with the presumption that introverts may know more people than non-introverts. Maybe they know a lot of psychiatrists. I don't know. But I'm going to start off with that presumption so that I keep it a two-sided test. I don't fall for the temptation to make it a one-sided test. Okay, so I'm going to get a piece of paper here so we can actually play with this. Should I do it on Excel? No, I'm going to do it by hand, I think, for the time being. Let me get this out of the way. See if I can't find my I'm going to have to dig it up again. Okay, here we go. And a fresh slice of paper here. Okay, first thing I do, first of my 5 steps is I set up my null hypothesis. Okay, so my null hypothesis is, my null hypothesis is that the mean number of close friends for the population is equal to the mean number of close friends for introverts. And that's my null hypothesis. My alternative hypothesis is the mean number of close friends for the population does not equal mean number for introverts. Okay, so I'm gonna actually come back to this later on and talk about what we might do to make this a one-sided test. Okay, so now I'm going to test that hypothesis. Well, I know that the mean for the entire population is 5.7. So I know mu is equal to mu p is equal to 5.7. Okay, so now really another way I could state my null hypothesis is that I could just call it mu introverts is equal to 5.7. That's my null hypothesis, right? I just substituted the mu p for the value I know, and my alternative would be mu for introverts does not equal 5.7. See, I'm saying exactly the same thing there. I'm just substituting the number that I already know is the actual number for introverts. Remember, this is a one sample test. One of these two sides I know already. When we get into Monday, we're going to get into situations where we're guessing at the real mean for both. Okay, and okay, so let's see the mean number, the sample size. Now the mean number, right now, X bar, we take 26 introverts, or whatever population it is, and we find that the mean for those 26, sample size is 26. The mean for those 26 is 6.5. Okay, so now I don't know, I'm going to assume for the moment that there's no reason to think that the standard deviation for either one of these would be different, right? So I'm going to use the standard sigma for the entire population was 1.3. I'm going to stick with that for my introverts as well, 1.3. Okay, so now I have to figure out how confident am I that the mean that I calculated from this that I found for this sample is really the mean of the population of introverts. Well, that's why I'm going to need my standard error, so I can see what the real range that I would expect the average to be. So my standard error is going to be equal to sigma 1.3 divided by the square root of 26, and that's going to be equal to judgment here. How much? 0.26. 0.26. Okay, so now I want to compare the two of these to see if I can say with 95% certainty, with less than 5% chance, alpha is equal to 0.05, that's my acceptable level of error. Okay, I want to see if I can, with less than 5% chance, if I can be certain, with less than 5% chance, if I can predict that there's a difference in these two means. Okay, means of the two populations. So now I could draw my confidence interval and see if that number's outside the confidence interval. I'm going to bypass that. I'm going to go right to calculating a z-score. And I'm going to say, how likely would I get this extreme of value, 6.5, that big a difference from the actual mean that I know, 5.7, if the standard error is 0.26, right? Well, what would be the z-score? How far away are these separated, are these two means? They are, that's going to be 0.5, 0.8 over 0.26 is going to be 3. I'm going to call it 3.1. That's a pretty big number for a z-score, right? Okay. So I could actually predict a probability. I could go to the table. I'm just going to guess that the table is going to find the p-value 0.002 or something like that. And I'm going to double it because it's two-sided. So I'm going to say the p-value is 0.004, roughly. I'm saying to myself. This is all well and good, except that I made kind of a little bit of an assumption here, and that is that the standard deviations of the two groups were the same. Okay, that's okay. That's not such a bad assumption. I'm sorry? I made believe. I didn't do it. I made believe I went to the z table, and that's what corresponded to a z-score of 3.1. Okay, I know it well enough to kind of have a rough idea. Right, I could be wrong. Maybe somebody at home actually did it. Okay, so now one of the problems I have here, let's say I didn't know what the standard deviation of the population was. I would have to depend on the standard deviation for my sample of 26 people. And let's say it happened to come out to be 1.3. Now, is that a large sample, 26? Not technically the way we're dealing with this. That's not a large enough sample for me to assume that the standard deviation is a good approximation of the population standard deviation. So now I have to make accommodation for that. I have to make accommodation for the fact I don't know the population standard deviation as well as I would like to, that this is introducing more error into our calculation. Okay, so now when I calculate a confidence interval based on having this standard deviation being equal to 1.3, instead of having it, based on the sample of 26, instead of having it based on a sample larger than 30 or the population standard deviation, I have to make an adjustment to the way that I calculate the confidence interval. And that adjustment is called a t-distribution. Okay, and what happens with the t-distribution? Clear this up. What happens with the t-distribution is, remember we have the standard normal distribution I drew this distribution, and I know that 95% of the outcomes, if I take a sample of a certain size, 95% of the outcomes are between 1.96 standard deviations below and 1.96 standard deviations above. That's if I have a perfect knowledge of the standard deviation, if I have a giant sample size, and so on and so forth. Let's say I have a small sample size. Well, if the sample size is equal to, say, 26, like in our case here, the distribution of the possible outcomes doesn't look quite like this. It's still bell-shaped, but now it's wider. So I got to go further out to include 95%. If the sample size is 10, well, that's another distribution that's further out, that's less certain. So I have to be certain that I got 95% possible outcomes, I got to go even further out. So a z-score of 2 for a sample size of 10 might be 2.3. A z-score of 2 for, excuse me, I'm sorry, a 95% confidence interval would require a z-score of 2.3 for a sample size of 10, let's say, but for a sample size of 26, it might be 2.1. And for a very large sample size, like 1,000, it might be pretty close to our 1.96. Right? So the sample size on the distribution is kind of funky, right? So now we're not going to have a table for every distribution. In other words, since every sample size has its own specific distribution, right? We would have to have a table like our Agresti table. We'd have to have a table like that for every sample size. Sample size of 2, sample size of 5, sample size of 20, sample size of 99, sample size of 500. We'd have to have an infinite number of sample sizes, tables. Instead of doing that, we either use a program which calculates it automatically. I'm dying to eat one of those cookies. We have a program size of of, uh, of a very large program size. We would either use a program to calculate what the values would be. That's what SPSS does for us, and Excel if we want to use it that way. Or we would have to have a summary for various sample sizes of what the important z-scores are. And that's what the t-table looks like. I'm going to open up a t-table now and take a look at it. Okay, go to the desktop. Yeah, we're going to have a table that summarizes the important values. It's going to look something like this. Take a look at this table. See, this table tells us if you want a 95% confidence interval, what area is in the right tail? 0.025, right? And that means there's 0.025 in the left tail. This they just happen to put it this way. Another table might look a little bit different, but basically what it's telling you is in each tail, including the right tail and the left tail, that for a 95% confidence level, you would have 2.5% in the left tail, 2.5% in the right tail for a two-tail test, right? And what it's going to tell you is this is the z-score that you would need in order to have that 95%. You know how you use 1.96? You would have to use this number instead of 1.96 to calculate your 95% confidence interval. So let's see our sample size. What was our sample size? 26. Let's go to 26. Okay, 26. But wait a second. Does this chart give us sample sizes? No, it gives us degrees of freedom. You remember when we were talking about degrees of freedom, when we were talking about variance? What was the number of degrees of freedom? It was equal to the sample size minus 1. So if the sample size is 26, degrees of freedom is 25, right? So we go to 25, and the 95% confidence, the z-score that we need for the 95% confidence interval, to calculate 95% confidence interval, is 2.056. I think that's the right column, yeah. I'm sorry, 2.06. It's a little bit more than 1.96, right? Now, what's going to happen if the sample size gets very large? If it gets very large, it gets closer and closer to 1.96. In fact, if the sample size is infinite, it is 1.96, right? So that's really where that 1.96 comes from. Okay, so now What we say is, when we use that sheet that's anything over a sample size of 30 is a large sample, that's because we're saying that once you get over 30, you're so close to that 1.96 that we'll just call it 1.96. We won't bother going to the table. However, if you have a really close call on accepting or rejecting the null hypothesis, you might want to consider that even though you have sample size over 30, it's going to the table. And like I said, the T table, the SPSS always uses the T score instead of the Z score. So these are called T scores. These are called critical values of T. Because what we're basically saying is that if you have a sample of size 26, in order to reject the null hypothesis, you have to be at least 2.056 standard errors apart in those two means. That's why they call it the critical value. If you're further apart, you can reject the null hypothesis, because the area is less than 2.5% on each side. If you're not further apart, you can't reject the null hypothesis. So in our case, what did I say it was? 2.06? In our case, when I calculate the confidence interval, in this case, if I don't know the population standard deviation, I use the sample standard deviation. Let me get back to it this way. If I don't know the population standard deviation, and I want to calculate a confidence interval for this, right? Well, I would have to say, well, a confidence interval, it's going to be equal to X bar plus or minus, since I'm looking at, it's going to be plus or minus the T score, right? For a 95% confidence interval, which is alpha over 2 equals 0.025. 2.5% is another way of saying 5%, times the standard error. Okay, so what's my T score? This time my T score, X bar, plus or minus, because the sample size is only 26, it's 2.06. 2.06 instead of 1.96 times my standard. Yes. You mean the T over here? That's T with alpha alpha over 2 equals 0.025. In other words, half of your alpha, in other words, half is in one tail. In other words, if your alpha, your acceptable level error is 5%, 2.5% of it is in the lower tail, 2.5% is in the higher tail. This is the same thing as saying a 95% confidence interval, or alpha is equal to 5%. Okay, but you don't have to worry too much about that. Yes. Yes. In other words, that negative 2.06 and positive 2.06. That's like your Z-score, except now you're calling it T.
These are really the same, the T and Z, if the sample size is big enough.
If the sample size is big enough, you make the assumption that they're the same and just use the Z-score. Because it can. In other words, it's more active. The real question is, why do we not use the T-score all the time? And the reason is because we're human and we don't want to spend all day with a pencil and paper trying to calculate this stuff. Because we're willing to accept estimating this in order to do our calculations. And we'd only be really concerned if it's a really close call. In other words, if you do this and it's clear that you have a sample size of 35, and your p-value comes out to be 0.01, 1%. It's so much less than 5%. You don't care that you use 1.96 instead of 2.06, right? So, but if we're a close call, you might be concerned. But in real life, we're going to most of the time in real life from this point on, if you were me in 1969 taking a stack course in the lab at Brooklyn Poly, and with the windows with the little wires in them and stuff like that, no calculator, no TI-19, and a slide rule and a mechanical calculator. If you were me, you'd have to go through the calculations yourself, and it would be important to you to be able to take that little liberty with the sample size. Now you're going to be using SPSS or Excel all the time, so you don't really need that crutch anymore. But we still say to ourselves, if it's less than 30, we're willing to take that estimate. But in real life, when you're doing real studies and stuff like that, you're going to be using software to count, unless you're just doing it to get an initial idea where you stand. You're going to be using software to calculate this stuff all the time. Is that chart we would use for the question on the homework to find the 90th percentile? Only, Jane, only if the sample size were less than 30, or if you didn't know the population standard. If you weren't dealing with a population, first of all, number one, we will only use the t-table when we're dealing with samples. That's number one, starter. And number two, we would only use the t-table in preference to the z-table if the t-chart in reference to the z-table, if if we didn't know the population standard deviation, or if we were dealing with a sample size less than 30. Okay, otherwise, we would use the z-table. So I hope that answers that question. Okay, so it's going to be x bar plus or minus 2.06 times the standard error. Anybody remember what x bar was at this point? It was 6.1 or something like that. 6.1, 6.5 plus or minus 2.06 times the standard error, which was point something, 0.25. I think it was 0.25, 0.26. Anybody want to tell me what that comes out to? 0.3. 0.536, call it 6.5 plus or minus 0.536. So that's going to be somewhere around 5 points. No, I got that wrong. 5 point half plus that, 5.35, something like that. 5.35 to 6.7 or something like that. Right, so that's our 95% confidence interval. Now that's different because we're using, we didn't use the population standard deviation, and you had to use 2.06. That's different from what we would have calculated if we had used 1.96, the population standard deviation. Where the hell did this t-test come from? Anybody knows the name of the guy that invented the t-test? And his name was not, it's called the student's t-test. And it's not because his name was Student. Okay? He was, I'm glad we brought up beer before. He was a bookkeeper, accountant, and statistician for Guinness Beer, okay, at the turn of the century. Okay? And if they wanted to, they were producing enormous amounts of beer. It was very important. There was a lot of money involved. This was big business. Guinness is like Apple, back in those days. I mean, beer was a major product back in those days. Okay, so now, if they wanted to know whether one yeast produced a higher alcohol content than a different yeast, right? One way they could do it is that they could try hundreds of batches. Let's say one. I'll put it in terms of like a one sample t-test. Okay, they may have been using a certain yeast for the last 10 years, right? Going back into the 1890s, and the one day, a chemist is riding in, with those big wheel bicycles in the front, big wheel, and he falls off and he falls on his head. He gets inspired and he says, I think we can use a different yeast and get a bigger yield, right? For the last 5 years, they may know that on the average, that their yeast will give them 6% alcohol in the beer. Okay, I'm going to call it 6 milligrams per cc, per milliliter, right? 6 milligrams per liter, rather. Is that 6%? No, that's 6 milligrams per deciliter would be 6%. I think no, 6 grams per deciliter would be 6%. Don't worry about the units, right? So now they want to test this new yeast to see if it gives them more alcohol. Well, the first time they try it, it may give them 5.6. Second time is 6.3. Third time is 6.8, and so on. But now, in order to really have a good idea of whether or not they're really getting more alcohol from this new yeast and comparing it, all they know here, they have mu here. They've been using this yeast for 10 years. They know what it gives them on average, right? Thousands of batches. But this one over here, how much beer are they going to waste testing this stuff before they know whether it's better or not, right? Well, as often as they do it, it's still a sample. So before he discovered a way of doing this with small samples, they would have to do an enormous number of samples before they were certain. They might have to do 50 batches or 100 batches before they were sure that there was really a difference, right? He came up with a technique for using the variability in small samples to help you decide how certain you are that there's a difference between the mean for this yeast and the mean for this yeast. His T distribution is a way to take a small sample and understand what the variability is, understand what the uncertainty is. So you can use a small sample and know what your probability of being wrong, know what your p-value is, and be able to tell whether it's less than your alpha is, less than your acceptable level of error. The reason why he published this under the name student is because Guinness apparently had some issues with proprietary information. Like I said, they were like Apple. Everybody's after their copyrights and stuff like that, right? So it's the same deal, except it was beer back in those days. So at any rate, they had a problem with somebody publishing something that caused them a problem and disclosed some of their recipes and stuff like that. So they had a hard and fast rule: nobody's allowed to publish while they're working for. But he convinced them that this mathematical technique was applicable other places. It was important to be published, so they allowed him to publish it, but under a pseudonym, under the pseudonym student. That's why it's called the student t-test. But his real name is William Gossett. William Gossett. Okay. All right. So let me ask you. Let's stop at this point and ask: do we have questions? No, I'm sure. There's a million questions. Right now, I posted assignment 4. Okay. I'm going to go back through it and see. I'm trying to remember how much of it involved the t-test, if any of it. I'm going to have to go back and take a look at it. If it didn't involve a t-value, I'm going to make sure that I add in a question or something like that. But you have access to it now. Making it so it's due on Monday. It's a couple of, it's like 15, 20 questions, but it's really just 3 or 4 problems. It's not a lot of work. Just like you've seen in assignment 3, there's a lot of questions, but I don't think a lot of you guys get through it really quickly. Okay, so I posted it, presumably, unless like there's really a lot of tears and anger and stuff like that. It'll be due Monday. If there is, you'll be able to talk me into doing it Wednesday. But again, you submit it then. If you submit it by Monday, you'll have an opportunity to resubmit it. So I want you guys to give this a try, to actually try and work out some of these problems. And keep in mind that really we're just now with this single sample t-test, we're doing something that's relatively simple. The z-score, you're going to calculate a z-score, is equal to an x bar minus the number that you know, the mean that you know, over the standard error, and then you're going to calculate what your p-value is. Okay, if you may in some cases need to use the t distribution. Now let's think about this idea of the z-score, calculating the z-score. Okay, so now I just mentioned that. Okay, I want to end up with this because this is going to come up. I just mentioned that, for instance, that we can calculate our z-score, right? It's going to be x bar, x, whatever the value you're testing, minus the mean over the standard error. Okay, let's say your sample mean turned out to be, I don't know, let's say 20. Minus the mean that you're comparing it to, let's say it's 10. And let's say the standard error turns out to be 5. It turns out to be 5. Your z-score is equal to 2.0. Does it sound like you're going to be able to reject the null hypothesis there? Right? What represents 95% certainty? 1.96 z-score. Z-score 1.96. This is bigger than 1.96. So that means the two values are farther apart than your confidence interval, right? So if you get a z-score this big, you're going to be able to reject the null hypothesis. If you got a z-score of 3, right? They're really far apart. Like, in other words, if we're 20 and the other value were 35, this would be a z-score of -3. That big a z-score means that they're really far. They're 3 standard errors apart. That's you're way out on the curve. That means the tail is really small, and you're going to be able to reject the null hypothesis. What you're doing there is you're looking at that value, that z value of 1.96. You're looking at it as a value that if you exceed that z-score, you know it's less than 0.05, the area on both, of both tails, right? So that's kind of like looking at that z-score as a critical value. Critical value because you need to exceed that difference in standard errors in order to reject the null hypothesis. Well, now let's say that you don't have a big enough sample to use the z-table. You have to use a t-table. Well, now you use the same formula, except you put t here. You say t is equal to x minus mu over the standard error, right? Well, let's say we were working with our sample of size 26, and it turns out that x was 20 and mu was a 10, and your standard error was 2, and that comes out to 2. Can you reject the null hypothesis now? You remember what the critical value of t was for a sample size of 26? It was 2 point. Yeah, that's our critical value now. Did we exceed that critical value? No, so we can't reject the null hypothesis. So now, a lot of times, rather than calculate out the exact p-value, like if you had the z-table, since you don't have a z-table where you can look up all the specific areas, all you can tell is for a sample size of 26, my 95% confidence interval is the area outside of a t-score of 2.06. So now you need to calculate the t-score in order to decide whether or not it's bigger than your critical value of t from that table for 95% certainty. Okay, I'm going to make sure that there's a problem in there. Okay, so now I'm going to assume that I have just absolutely confused everybody that's listened to this. And I'm going to depend on the homework to be a mechanism for you guys to give it a try and actually apply some of these formulas. I'm going to see if I can't find, I'm pretty sure somewhere or another that we have a table, a paper we put together that has the formulas summarized.
Okay.
So yeah, and maybe I'll give you an example for each different version. Yeah, each way you might approach it. Yeah. Yes.
So anything that's outside of that area,
yes,
would make it bigger.
Yes, because it's so far apart, you can say that with a lot of certainty that they're really different.
So is it right to think about like when you 2.06 everything with all the area within the
That's your confidence. In other words, for a sample of size 26, your confidence interval would be everything that's inside of 2.06 standard errors to the left of the mean and 2.06 standard errors to the right. That's going to be your confidence interval for a small sample instead of 1.96 on each side. Yeah, your confidence interval, if you calculated your confidence interval for a sample size of 26, you would say that it's x bar plus or minus 2.06 times the standard error, right? Everything within 2.06 standard errors to the left of the mean, the sample mean, and the right of the sample mean. That's the range within your 95% sure that true mean is going to be between those two. And the reason why it's further apart than 1.96 is because you're working with a small sample size and you don't know the population standard deviation. Okay, that's the function of that t-table, is to give you that extra buffer you need to account for the fact that you're working with a small sample. And in fact, as the sample size gets smaller, the t that you need to exceed gets bigger and bigger and bigger. And your confidence interval gets wider, right? Because if you're less confident, remember, it gets wider because you got to make up for uncertainty, right? The wider you make it, you're doing that so that you're making it wider to increase your level of certainty.
If the t was 2.5, you can reject her?
Yes. No. If it were 2.07, you could reject. If it were 2.09. Now, I'm waiting to see who. 2.5. No, 2.5 is greater than 2.06. So you can reject because it's bigger than your critical value. You're outside of that. confidence interval. I'm sorry, you're saying if your t
2.5, 2.5.
if the t that you calculate,
The T's
x bar
2.5.
minus mu over standard error, if that number is 2.5, you can reject, because that means that the two means, the x bar and the mean, are far enough apart that you're outside of the confidence interval, which would have been 2.06 for that sample size. In other words, if remember our confidence interval, our confidence interval was 1.96 standard errors to the left and 1.96 standard errors to the right. And if you're comparing it to a different mean of the population you know, and it's outside of that range, further than 1.96, like 2.1 or 2.5 standard errors out, then you can reject the null hypothesis. When we're using the t-test, right, instead of 1.96 for the sample size of 26, now it's going to be 2.06 and 2.06 on both sides. So now, if you're inside of 2.06 standard errors, you can't tell you can't say it's different than the mean than in that range. But if you're outside of the 2.06, so if it were you calculated 2.05, then you could reject the null hypothesis. It's far enough out.
How is it all to
2.06.
Yeah.
2.0, it's not 2.6, 2.06. It's greater than, it's outside. Another way, here, let me draw it.
If it was less than,
Yeah, let me draw it. And we'll call it a night then. Okay, I'm going to draw a confidence interval, right? If I know the population, if I know if a big sample size, or if I know sigma, right? If I were take a sample of size 100, let's say, right? And I calculate my standard error is going to be 1, right? Because sigma over the square root of n. Standard error is going to be 1. Let's say my sample x bar is equal to 20, right? So 20 is in the middle, and 1.96 standard errors to the left, and 1.96 standard errors to the right. My 95% confidence interval is 1.96 a z-score 1.96 standard errors to the left of 20 and 1.96 standard errors to the right of 20, right? Because it's, because it would be 20 plus or minus 1.96 times 1 as it happens here, okay? If it had been standard error 2, it would be 1.96 times 2. So in this case, it's 1.96. So now, if I compare this to another population where the mean is equal to 23, right? Well, what's the z-score of 23? The z-score is going to be equal to 20 minus 23. I'm sorry, 23 minus 20 over the standard error, which is 1. The z-score is going to be 3. So where is that value? It's all the way out here. It's outside the confidence interval for what your mean for population number 1 was, based on the sample. The known value of the other population is outside of that. So now, if this sample size had been 26 instead of 100, well, the number of standard errors outside would have had to been 2.06, not 1.96, but it has to be a wider range. But if I'm looking at the same thing here, a 3 standard error difference, it's still outside of that range, so I can reject the null hypothesis. Oh yeah, she's saying. I would think she says
2.05.
Oh, I thought you said 2.5.
2.5.
Oh yeah, 2.5. She said 2.5.
I thought she said.
See how much time you killed here now?
Okay, this is on me.
Yeah, you're right though. If it were 2.05, you would not have been able to reject the null because it was less than 2.06. In that regard, you're right. Absolutely.
2.5.
Right. Yeah.
You reject 3 because it's bigger than 1.96.
Well, if I have a big sample and I reject it because it's greater than 1.96. If I got a small sample of size 26, I would reject it if it's bigger than 2.06. If I had a sample size of 10, anybody got the table handy and let me know what 9 degrees of freedom, what it is? For 9, what is T for 9 degrees of freedom? 2.26. In order for you to reject the null hypothesis, if you have a sample size of 10, right, then you'd have to be more than 2.26 standard errors away from your sample mean, right, with the number that you're comparing it to. Okay?